Hi everyone. Let's go ahead and do a review of some of the things that we skipped over in 5.1 to 5.3 before the break and add on some new things about 5.4 today. So jumping into some of those pre-break topics, we had skipped over the questions that looked like this. They are questions that you will see on the AP exam, and they're quite easy once you get a hang of it. So I want to go over that now. Remember that we started with the Riemann sum approximation, and you'll remember that we formalized this, which is really the width of our rectangle. So that's our delta x, and we formalized that with our dx, and then we were summing, and we formalized that with our integral notation once we learned that. So keeping that in mind, our dx is going to be 1/20th. That means that the width of our rectangle is going to be 1/20th. Now, where are we going from and where are we going to? So always think of these as kind of right endpoints, okay? That's the easiest way to think of it, I think. Let's start all the way here. 20 over 20 is 1, so that means we're going to 1. And where are we starting? Well, our width is 1 over 20, so 0 plus 1 over 20 is 1 over 20. Stick with me for a minute. The second one's going to become easier. We go from 0 and we go to 1, and each sub-I, each new rectangle place that we're at is going to be 1/20th over. So we have 1/20th, then 2/20th, then 3/20ths, all the way up to 20 over 20, which is 1. You see how that's happening? 1 over 20, 2 over 20. Because remember, these are right endpoints. Okay, we're going to use width times the height, 1/20th. Width times the height, 2/20ths. Width times the height, 3/20ths. Okay, now what are we doing at each of those? At each of those, we are squaring it. So our function is going to be something squared. Okay, we were doing f of x sub I, the ith one, squared. Now, this 1/20th was just our delta x. So that's captured in the dx already, okay? So you don't need another 1/20th times. Definitely don't need a 1/20th times. All you have is you're summing up all of these times dx. So you can eliminate a, b, and e. So now which one is going from 0 to 1 and you're just squaring the function? Well, that looks precisely what C is saying to you. All right, let's go to the next one, and I think the next one will be easier. Same type of thing. So now you see that our delta x is going to be 1 over 30. We're going from 0 plus 1 over 30. So we're going from 0 to 30 over 30, which is 1. And what are we doing to each of those? We're taking the square root. So the 1 over 30 was our delta x, and then we're adding up all of these. We're going from 0 to 1, and we're just doing the square root. That's exactly what it's asking us. Now let's do another one. So in this one, our delta x is going to be 1/10, and we're going from 0, right? Because it's 0 plus 1/10, 0. The next one's going to be 1/10. The next one's going to be 2/10. And now we're going to 20 over 10, which is 2. So in this one, we're going from 0 to 2. 0 to 2, 0 to 2. Nope, can't be this one. Nope, can't be this one. And what are we doing to each of these? Well, it looks like nothing's happening, right? We're not squaring it. We're not taking the square root. It is just itself. It is just x. Let's keep going. Okay, now this one's generalizing it. Our delta x now is going to be 1 over n. Now we're going from 0 plus 1 over n. So our first one's going to be 0. Our next one's going to be 1 over n, 2 over n, 3 over n, all the way to n over n, which is 1. So we're going from 0 to 1. Well, all of these were 0 to 1, so we can't eliminate anything. And what are we doing to it? We are squaring it, right? So we're just squaring it. Could be that one, could be that one. But all this 1 over n is the delta x. So I don't know why that one has a 1/2. That's definitely not our answer. That's all we do. The reason we have the limit as n approaches infinity is just means we're getting more and more and more rectangles underneath the curve. And the more rectangles we have, the better the approximation is going to be. Go ahead and pause right now and try this one on your own. Okay, now that you've had a little bit of pause, hopefully this is what you were thinking. So this 1 over n, again, is going to be my delta x. My start is 0 plus 1 over n, so I'm starting at 0, and then I'm going 1 over n, 2 over n, 3 over n, and now I'm going to 2n over n, which is 2. So I'm going from 0 to 2. All right, that eliminates that one and that one. And then what am I doing at each of these? I'm just taking the square root of it. That's all I'm doing is taking the square root of it. So B would be my answer there. All right, now that we've gotten those down, let's try this question, which was number 10 on your quiz review. So it said a 12-meter long tree trunk with circular cross sections. Okay, so the cross sections are going to be circular, and they're giving you a diameter here. The distance above the tree trunk is measured from the ground, and dx represents the diameter of the points. Write an integral expression in terms of dx that represents the volume of the tree trunk between x equals 0 and x equals 12. Okay, the volume, think of it as you're adding up, which is the integral, all of these areas. We're going to get much more into this later, but kind of think of it like this. If you have a loaf of bread and you wanted to find the volume of that loaf of bread, right? It's an irregular shape. You can't just do the length times the width times the height. But if you cut that loaf of bread into all these little slices, say that the slices were so thin, you could easily find the area of each of those slices, right? Because each of the areas, if you just cut the bread, the cross section would be a square, pretty much, more or less. And if you added up all those areas, wouldn't you kind of get the volume? Anyway, we're going to be talking a lot more about that as we go on in the year. But the volume is pretty much just add up all of the areas of the cross sections of each of the slices, and then you would get the volume. So if you're with me on that step, then we're adding up from 0 to 12. And how do you get the area? Well, the area is the cross section, it said was a circle, right? So the area of a circle is pi r squared, but we have a diameter. And so the diameter over 2 is our radius, right? Our radius is the same thing as diameter over 2 squared. So if we simplify that, we're going to get pi over 2 squared is 4. So pi over 4 d squared. I'm just going to write it like that. So 0 to 12 of the areas, pi over 4 d squared dx. I'm going to take that pi over 4 out because it's a constant. Integral from 0 to 12 of d squared dx. So that just said write an integral expression. And then part B says approximate the volume using the data from the table and midpoints. So what we're going to be doing with midpoints, since I have a data table here, I am going to have to extend my width. And that is going to be my first one, that is going to be my second one, and that is going to be my third midpoint. That's the best that I can do. Don't forget though, it's asking us d squared. So this is d, we've got to do width, which is 4. 4, they're actually all 4 in this case, so I'm going to factor it out. It's only because they're the same everywhere. It's a 4, and a 4. If they weren't the same, you would have to multiply separately. And then d squared, so not 1.5, but 1.5 squared plus 1.42 squared plus 1.38 squared. And then I don't have a calculator with me right now, but you know what? It's okay. I can leave my answer like this. Maybe I'll simplify a little bit. 4 and the 4 I'll take out, so I'll leave the pi. 1.5 squared plus 1.42 squared plus 1.38 squared. It's fine to leave your answer like that. If you have units, you need units. And the units, this is meters times meters squared, right? And so that's going to be meters cubed for volume. And that's my final answer for part B. And then explain why there must be a value, x, between 0 and 12 such that d prime equals 0. All right, hopefully you see this as the mean value theorem, that the slope has to be equal to the derivative somewhere. And since this is a real life example, this tree trunk, it's going to be continuous and differentiable, right? You can't just jump data somewhere. Mean value theorem, remember, you want to think to yourself that the slope equals the derivative somewhere. So, is that true? Let's look at our data. Here it's 1.5 and here it's 1.5. So since the slope between 2 and 8, okay, the slope between 2 and 8 is 0, you know that somewhere between 2 and 8, f prime of c equals 0, because the slope between x equals 2 and x equals 8 is 0. I wrote that really informally, but we just chatted it out, that the mean value theorem says that the slope has to be equal to the derivative somewhere. And because they're asking, is it true that d prime equals 0 somewhere? You're just looking for somewhere where the slope is 0. So the slope is 0 when the y2 minus the y1 is 0, right? You want a 0 in the numerator of the slope formula. And so since I can find that to be true, I know that since the slope equals 0, the derivative must be 0 somewhere in that interval. We'll talk more about that one too. Hopefully A and B made a lot of sense. You've seen a lot of these interpretation questions recently. I just want to make sure these are golden and you're really good with them because they're very, very important. So let's break this one down. It says, suppose a water tank initially has 7 liters of water. So that means via 0 is 7. It tells us that in this problem too. If RT is the rate in liters per minute at which the water tank is being filled, what does 7 plus the integral from 0 to 6 of RT dt represent? All right, let's just start with this. If we break down that integral, the integral from 0 to 6 of r of t dt, r of t is the rate at which the water tank is being filled. So its antiderivative is just going to be the volume, right? So the antiderivative of r of t is v of t, and we're going from 0 to 6. So that's v of 6 minus v of 0. V of 0 is 7, so that's v of 6 minus 7. Okay, so that's this part. So now if they ask us, what does 7 plus the integral from 0 to 6 of r of t dt represent? We can replace this part with this, right? So let's go ahead and do that. So it's just v of 6. This is the volume of water in the tank after 6 minutes. Think of it like this. This is the initial amount, and then you're adding the area from 0 to 6, right? So it's like you're starting here, and then you're adding however much more is being pumped into the tank between 0 and 6 seconds. So this is how much water you have in the tank after this full 6 minutes. And what is it measured in? Measured in liters, right? Because that is the volume is measured in liters. The rate is liters per minute times the delta t time is measured in minutes. Liters per minute times minutes is liters, okay? Julia's revenue is RT $1,000 per month. Julia receives a $3,000 signing bonus. How much money total has Julia made by the end of the first 6 months? It says RT $1,000 per month. So when we have $3,000, that's just 3 because this is in thousands of dollars per month. So our initial, let's say her money initial at time 0 is 3. How much money has she made at the end of the first 6 months? So pretty much you want to find m of 6. And the derivative of the amount of money she gets is our revenue, right? This is the rate that she's getting it at. So I'm going to just say m prime of t is this revenue function, since I just randomly called this m for money, the amount of money she has. How do you know what to put on your integral? You know something about 0 and you're trying to find something about 6. It might make sense to use those as my bounds, okay? That's pretty much all I'm thinking right now. I know I'm going to take the antiderivative of the revenue function, and the antiderivative of the revenue function is the same thing as the antiderivative of m prime of t, right? Revenue and m prime of t are equivalent. So I'm going to just replace RT with m prime of t because they are equivalent. And the antiderivative of m prime of t is m. The antiderivative of m prime brings us back to m. If you could have leapt from this step to this step, right away, go for it. You do not need to write this step in between. I just wrote it to talk it out. So now we're evaluating that between 0 and 6. So that's going to be m of 6 minus m of 0. And I know that m of 0 is 3. So if I want to solve for m of 6, which is what I'm trying to do, then I know that this equals this. Okay, let me just rewrite it again. Integral from 0 to 6 of r of t dt is equal to m of 6 minus 3. Add 3 to both sides and you get m of 6 equals 3 plus integral from 0 to 6 of r of t dt. Because pretty much you're saying this is the initial amount and then you're adding on whatever money she makes. Okay, this is her rate that she gets it at. The antiderivative of it is going to be the amount that she gets. The antiderivative of the rate is going to bring us to the amount, right? And so remember that you have to add the 3 because that's the initial amount that she has. You're starting at 0, but she had $3,000 to begin with. So you can't forget to add that initial amount. All right, just for a little bit of fun here. F of z represents the number of flubs when the level of Zorks is z. Then the integral from a to b of f of z dz has Units of what? What are the units? So I'm going to just start with something that you know, and then let's try and figure that out together. So you know that the antiderivative of v of t dt is measured in something like meters or feet. Let's say our velocity function is measured in meters per second for this example. Our time axis would be measured in seconds. So the way, say that's a velocity function, that you get what its antiderivative is measured in, because remember the antiderivative is the area under the curve, it is literally length times width. And the units are literally width, which is seconds, times the height, which is meters per second, measured in meters, okay? So that's kind of what we want to be thinking about when we do a units type of thing. So in this case right here, f of z represents a number of flubs. So we are going to have some function. Here's my f of z function and number of flubs when the level of Zorks is z. So Zorks are on this axis. And so the antiderivative of this f of z dz is just going to be base times height, which is going to be Zorks by flubs. And so that's it. This unit for this is a totally made up example just to be a little bit silly, but also to show you how easy it is to figure out units. You really just do base times height, because that's how we find the area. And remember that this integral, it's so important that you remember that this integral is the area under the f of z curve. So important that you remember that, what it means. So while we're being silly, let's keep being silly. F prime of z represents the number of flubs per Zork, which makes sense, right? If this was flubs and this is Zorks, then its derivative is going to be flubs per Zork, just like the position function would have been meters and seconds, and then the velocity function is meters per second. If you look at velocity, it's meters per second, and the acceleration is going to be meters per second, right? Because we're doing delta y over delta x to find its derivative. So let's apply that same thing here, and now we have our f prime of z curve, and that's going to be flubs per Zork on this axis, and we're still going to have Zorks on this axis. And so the antiderivative of f prime of z dz, that's just going to be, again, our width times our height. So that's going to be Zorks times flubs per Zork, and those are going to cancel out, and so we just have flubs. It's going to be measured in flubs. And what does that represent? Well, let's look at it. A to b f prime of z dz. Well, the antiderivative of f prime of z is going to bring us back to f of z, right? And we're evaluating that between a and b. So that's just f of b minus f of a. It represents the change f of b minus f of a in the number of flubs, right? From Zork A to Zork B. Usually you say from time A to time B, but you know, that axis is Zork. So it represents the change in the function. Our function is flubs in this case, okay? So that's the important stuff. It represents a change in an amount, okay? It's not a rate now, it's the change. Flubs when the Zorks are B minus the flubs when the Zorks are A. Okay, enough silliness. Let's get into something real. I just wanted you to see for now, we are not doing this, but I just wanted you to see what an actual AP problem looks like. This is what one of the free response questions will look like, where you have a graphing calculator for this particular question. It will be split into A, B, C, and D. We can actually do a lot of this problem at this point. We're not going to, but you can see how similar this looks to that data one that we were doing a little bit earlier, where we have to use the data to interpret W prime of 12. So we want to find the derivative at the point 12. And then we want to evaluate the antiderivative of the W prime function using correct units, interpret the meanings. You can see that this is why we've been practicing this. Now it says use a left Riemann sum with 4 subintervals to approximate this. Okay, so that's why we just practiced that also. And then another interpretation type question. Okay, so this is going to be a 9-point question, and you will have 6 of these free response questions on your exam along with the multiple choice portion. This is what it's going to look like, and we're almost at the point where we are able to solve full free response questions, so we'll be getting to that. I found this little graphic, and you know how much I like graphics and comics, in a book that I was reading, and I just thought it was really clever. As long as the integral between morning and evening of mood function of s ds is greater than 0, you're doing okay. And so what does that mean? I guess that this is her mood function, and then the area under the mood function, as long as it's greater than 0, it's greater than 0 as long as what's above the curve is greater than what's below the curve, right? Because the integral is going to be measured by whatever is above minus whatever is below. And so you want that to be positive. You want the euphoria to be greater than the agony. So I thought that was kind of cute. And just a good little reminder of how you approximate all this stuff, right? You're doing the area above the x-axis minus the area under the x-axis. And that's how you calculate these integrals by hand if you don't have actual data or you don't have an actual function. Now let's get into some of the new stuff. So you want to remember that the derivative of the antiderivative pretty much brings us back to the function itself. So this is a very simple one, the derivative of the integral from 4 to x. That is just going to be, plug that in here, cosine x to the 5th, and then you would want to chain whatever this is. That is just times 1, so you don't really need to worry about it. And then the 4 is going to drop off because the derivative of 4, it's a constant, and so that would bring you to 0, right? That's the fundamental theorem of calculus. I'm going to prove it in a second. So it works like that because let's say we have this big G function, and that's the integral from a to x of f of t dt. All right, the fundamental theorem of calculus says, well then, the derivative is just going to be the function itself. The derivative of the antiderivative is just going to be the function itself evaluated at x, okay? That's FTC, but let me prove it. Let's work this out. The antiderivative of little f brings us to big F, right? And we're evaluating that between a and x. And so that would be big F of x minus big F of a. So if that's g of x, then what's g prime of x? We're going to take the derivative of big F minus the derivative of f of a. Remember, a is a constant. So the derivative of a constant is just going to be 0. X is not a constant. A is a constant. The derivative of a constant is just going to be 0. Now the derivative of big F is just our little f minus 0. So that's how we prove that. That's our simple case. Now let's do our more complex case. So say now that we have another function, I'm going to call it g again, and that's an integral, let's say from a to x squared of f of t dt. The fundamental theorem of calculus says that the derivative of the antiderivative is, you're going to go ahead and you're going to put this in, and then you're going to chain it. So f of, put that in, x squared, and then you're going to chain it. That's what the fundamental theorem of calculus says. Let me prove it. Let's do the same thing. The antiderivative of little f is big F, just noticed that was supposed to be a t, evaluated between a and x squared. So that's going to be big F of x squared minus big F of a. Now when I take its derivative, the derivative of big F, f prime, leave the baby inside, but you've got to chain, right? Times the derivative of the baby. And then the derivative of a constant, again, is 0. So that's why it's dropping off. Big F prime is just little f, x squared, times 2x. So that's why, see, we're plugging in this, and then we're taking the derivative. And so that's why we always chain whatever the bound is. So chaining this bound is 2x. Chaining this bound is 0. Derivative of a constant is 0. So that's why it drops off. So that is really important, that you understand why the fundamental theorem of calculus works. Let's continue to practice. Let's try this question again. Hopefully it makes more sense now. That is our variable, and then this constant's just going to drop off. And so the derivative of the antiderivative, go ahead and put this in and then chain it. So we just get cosine of x to the 5th. We're going to do a bunch of these in a row. This one, we're going to put the x squared in, and this is going to drop off, right? So we have, instead of 1 plus t cubed, we have 1 plus, we're going to put that x squared in, cube it, and then you've got to chain. And what we're chaining is this. Don't get it confused. Now this one actually has 2 bounds. So I'm going to have an x cubed as my top bound and an x as my bottom bound. So I'm not just minusing 0 in this one. I'm going to be first putting in the x cubed, square root of 5x cubed squared plus 2. Chain it, okay, because that was that one, minus, just like we did before, and now not minus 0, put in the x, 5x squared plus 2, chain it if you want. You don't need to write that. I'm just writing it, okay, because of that one. Okay, next one. Two ways to do this one. The first one would be to do it like we've been doing it, except the constant, the 0 is going to be first, right? So we have 0 minus, and then we put in this x squared. So we would get minus secant squared x squared, and then we got to chain this times 2x. So our answer is negative secant squared x squared times 2x. And the other way to think of that is to rewrite this. Remember that the integral from a to b of f of t dt is the same thing as negative integral from b to a. So let's just remind ourselves of that. And so you could flip this over and write it the way you normally see it, with the 5 on the bottom and the x squared on the top, if you take the negative out, right? Because it's the opposite. And so if we were to do that, you're obviously going to get the same answer. Now you have that negative, let it hang out, and then you would be putting this x squared in and chaining it. Secant squared x squared times 2x. So either way you want to do that one is fine. And that's kind of why we get this opposite formula, because you would be doing 0 minus on that one, or flip it first. Either way. I know there was a lot packed into this lesson, but hopefully this clarified some topics from before break and got your mind prepped and ready for this unit ahead. And that's all for this lesson. Bye.